is going to be a review section. So here, the idea is because you guys have done college algebra as a prerequisite for this course, we're not going to spend too much time, going over complex numbers. But I again want to make sure, because it's probably been a while since you've worked with complex numbers, that we give you a good base on it, so that when we move on to the next sections, you guys are at least comfortable working with complex numbers. So remember, when we get into complex numbers, this means we are actually now talking about real numbers along with imaginary numbers, because when you think about the breakdown for complex numbers, and sometimes people use the term complex numbers when they're talking about just imaginary numbers, but technically complex numbers is the big set. So that's actually the bigger family, the bigger group, where you have complex numbers, and that breaks down into real numbers and imaginary numbers. So real numbers and imaginary numbers are actually the subset of the bigger, complex number set. So they kind of break down into two separate parts of it. So like I said, sometimes textbook will use complex numbers terminology when they're talking about imaginary numbers, but technically real numbers are also complex numbers, because they're subsets of those. Alrighty, so let's get into, when we talk about imaginary numbers, this is a great example, because for imaginary numbers, the idea is, when we try to solve an equation like this, you are actually ending up with, when you try to isolate that x squared, you move the 1 to the other side, and you end up getting -1. Now, when we end up taking square root on this, well, you will end up with plus or minus square root of -1, and you can try plugging in that square root of -1 into your calculator, and let's see what Desmos says. So, okay, need to do it backwards. Okay, you will see it gives you an undefined. If you try to do this on a handheld calculator, it should give you, I think, an error message or domain error or something like that. So as you can see, we are not able to take a square root of a negative number. And this is true for all negative numbers. You could have had a -4 in there and you would have still run into the same issue. Because this happens, anytime you try to take an even root of a negative number. So you can try to take the 4th root of a negative number, the 6th root, 10th root, any even radical that you will have, you're going to run into this same problem. So this is kind of where, we start defining imaginary numbers, because your real number set is just not enough to simplify this problem. So that's where we get into this definition, where we define the imaginary number I as square root of -1. So technically, this answer will actually come out to be positive or negative I, because that square root of -1 is defined as I. And the idea is, when I take I as square root of -1 and I take a square on both sides, because we know square and square root will cancel each other out, you will see that your I square will then actually be defined as -1. And that's where this definition is coming from. So now, once we bring this idea of imaginary numbers in, then, it expands our, basically it expands our, repertoire. We're able to solve a few more of these equations that we would just not be able to solve with only real numbers. So here, you can kind of see, we're getting into some of the details, and I'm hoping you're familiar with some of this. So now that we are adding real numbers with the imaginary numbers together, we end up with complex numbers. The standard form for a complex number is a plus bi, where a is called the real part, because as you can imagine, that doesn't have the imaginary number I on it, right? So that becomes the real part. And the bi, because that does have the imaginary I on it, that becomes your imaginary part. So your complex number is a combination of the real and imaginary numbers put together. Now, if the B value comes out to be 0, so if you end up with A plus, 0 times I, well, 0 times anything will become 0. So that's how you end up getting only real numbers, right? Because that means your imaginary part is basically 0 and it doesn't show up. So that ends up giving us, these real numbers over here. For the imaginary numbers, you can have both A plus BI. Or if A happens to be 0, then, this guy will disappear and you'll just be left with BI, which will, give you the imaginary part. So technically the imaginary part can be the whole thing, or it can just be the BI where your real part is 0. So it kind of works, with both ways. Now they're just showing you how you can write these out in the standard form. So let's say if you were given -5 plus square root of -9, we actually end up breaking that square root of -9 into 2 parts, because you separate that negative by using -1, because, of course, -1 times 9 gives us -9. But if I separate the square root of -1 from the square root of 9, well, square root of -1 we just saw becomes the imaginary number I. Square root of 9 gives us 3. So you actually end up getting 3i, and that 3i is, your imaginary part for BI, and the -5 is your A part. So A plus BI. So that's kind of how you convert these complex numbers, if they're given to you with the radicals, into the standard form of your complex number. Anybody have questions at this point? Everybody's okay? Alrighty. So just your formal definition for the complex number. So you've got technically A and B both are going to be real numbers. It's that addition of the I that will convert that second part into the imaginary part. So they're saying, again, the real number A is your real part, the number BI, where B will be a real number, becomes your imaginary part. When B is 0, you get a real number. When B is not 0, you get the imaginary number. And then they are saying the number of the form BI, and this is where, your A is 0. If you just have the BI, that is your pure imaginary number, because now it doesn't have that real part, being added to it. Alrighty, so they're talking about how your two complex numbers can basically be equal to each other. And that means, if we are saying A plus BI is equal to C plus DI, then obviously it means literally A and C have to be the same number, and B and D have to be the same number. So it's literally got to be like you had above, the -5 plus 3i will basically be exactly equal to -5 plus 3i. So equality between two numbers. Now let's talk about operation. So this is where we're getting into addition and subtraction of these complex numbers. Just an interesting example that your textbook talked about, where complex numbers are involved. And one of those is this fast Fourier transform application. And if you guys are planning on getting into engineering, you will actually be working quite a bit with complex numbers, especially in electrical engineering. I believe you see a lot more complex numbers. So in this case, I ask you guys to think about this, how you would add in algebra. So, if you had a number like 3x plus 2, and you were being asked to add this to, I don't know, -7x, I don't know, -5. So you know how we would combine the x with the x when we talk about like terms, and then we would take the constant with the constant. You're actually going to use that same idea here when you're adding and subtracting these complex numbers. So literally, the real number parts will get added together. So the A gets added with C, and then the I imaginary parts, right? So that means the B will get added with the d, and you keep that I as it is. Because think about this. If I add 3x with negative 7x, of course, my x would stay the same, and I would do 3 minus 7, which would give me -4. So that would be the same thing that happens here with imaginary numbers, or the imaginary part. Now, one thing you want to be careful about is when you are subtracting these. So you can see we have a plus bi minus c plus di. So this is where I actually think about the distributive property. So you take that negative sign and distribute it inside your second number. So you will basically end up with a plus bi for that first number. And then once you distribute that negative sign, that would be negative c. Positive times negative is negative, so that will become negative di. So you end up doing a minus c, and you end up doing bi minus di. So a minus c, of course, is here, and this guy will become b minus d. Keep the I on the outside, and that's where they're getting the second part from. So I actually think more in terms of, algebra as, oh, there's a negative sign here, go ahead and distribute that into your second number, and you'll be able to get your answer from there. So they've just got some basic examples over here, kind of walking you through the addition and subtraction. This property little over here that they're talking about, the additive identity in the complex system number is 0. So they're saying, the same as it would be in your real number. So the idea is, if you're going to take a number and add it to its own additive inverse, so it's kind of like adding 3 with -3, you would end up with 0. That's the same thing that happens here. So your original number would be a plus bi. Its additive inverse would be the negation of that, right? So negative, take that and distribute that. So that would give you negative a, negative bi, which is your additive inverse for the original number a plus bi. And then when you add those two numbers together, you will end up getting 0. So that's kind of what they're talking about here in this little property here. So actually, let's go ahead and pick an example for this addition and subtraction. Actually, we need to get into chapter 4. There we go. And just a quick So we'll keep it simple, and let's do 9 and 12. So for number 9, you have 5 plus I being added with 2 plus 3i. So again, since this is addition, you don't have to worry about any negative signs. We can just go ahead and write these out without the parentheses. And again, it's like combining like terms. So we will take 5 and add it with 2, and then we'll take the I terms and add them together. So 5 plus 2 will of course give us 7, and then 1i plus 3i will end up giving you 4i. So really just as simple as that. And you don't even have to spread it out. I mean, you can literally go from here and you can say, oh, 5 and 2 will go together. I and 3i will go together, and I'm going to end up getting 7 plus 4i. For number 12, we had 3 plus 2i. Now, since this is subtraction, we will definitely need to clean this up a little. And then 6 plus 13i. So this one, I definitely want you to go ahead and distribute that negative sign, which will end up giving us 3 plus 2i will stay the same. And then negative will make the 6 a negative. The negative will also make the 13i into negative. So what will this answer come out to be, guys? Okay, I'm seeing a couple answers coming through. Alrighty, very nice, guys. So I've got Savannah, Darren, Andrew, Lucy. Perfect. So we've got 3 minus 6. So you will combine these guys together, and then you will combine these guys together. So 3 minus 6 will give us -3. Positive 2 minus 13 will give us -11i. Everybody okay on that? Anybody have any question on this? Yeah, everybody's okay? Alrighty, perfect. All good? Okay, very nice. Okay. And as you can see, there are a few more examples in here if you just wanted to get a little extra practice. They're just again emphasizing a little bit of the properties that we work with real numbers, how they actually also work with complex numbers. So they're talking about the associative, commutative, and the distributive property over addition over here. So in this one, they're actually talking about what happens when you multiply two complex numbers together. So, again, guys, FOIL is your best friend when it comes to these kind of numbers. So you can see they're taking the number A and they're multiplying it with the entire second parentheses. So, A will multiply with C and DI, and they're doing the same thing with BI, and they're multiplying it with that second parentheses. Now, if you think about this in terms of FOIL, then, we would multiply A times C. So you've got A times C. Then we would multiply A times DI. So that's your A times DI. Then we would go with B times, BI times C. So BI times C is over here. And then we would do BI times DI. And BI times DI is actually what is giving you this guy over here. And that's coming from right here. Because when you multiply BI times DI, well, of course, we do B times D. And then I times I will end up giving us I squared. But as we just saw above, when we describe this, well, we know I squared comes out to be -1, right? So I squared comes out to be -1, which means when you clean this guy up, you basically are taking BD times -1, which is what they had over here. And -1 will, of course, convert these into a negative BD. So that's actually what happens over here. And this will be true for any time you are multiplying two complex numbers. That last term from your FOIL will actually end up converting to a real number. And then you will be able to combine these two terms together. And you'll be able to combine these two terms together, which will come out to be, another form of A plus BI, because it will all clean up. So that's your, distributive property, but basically it comes down to working out like the FOIL method. And then they're talking about the commutative here, because commutative, remember, means you can switch the order of your numbers, but they will still add up. So I can add 3 plus 5, or I can add 5 plus 3, and I'll still have the same answer. With associative, we talk about group. So even if you change your grouping, it will come up the same answer. So they're just kind of highlighting that those properties for real numbers will also work with complex numbers. So you've got different examples over here showing you how to multiply complex numbers together. So this one is, just taking one single number and multiplying it with a complex number. So, basically using that distributive property to multiply. This will, of course, be the FOIL method. Here you can use the FOIL method, or remember, we kind of talked about this before when we had talked about conjugates. When you're multiplying conjugates where, the terms are the same, it's just the plus or minus in the middle that's different. This breaks down into A squared minus B squared. So that's actually the same thing that happens here. You multiply the 3 and 3, which is our a square, minus your b square would be 2i times 2i, so 2i squared. 3 squared becomes 9. 2 times 2 is 4. Of course, I squared, but then we know I squared becomes -1. Negative times negative will end up becoming positive. So you actually end up with 9 plus 4, which ends up giving you 13. So in complex numbers, you can actually modify this to, if you have a plus bi being multiplied by, with a minus bi, this actually changes to a squared plus b squared. And that's what you will end up with when you do these multiplication of conjugates. Now, the last one over here, you're actually multiplying the same number into itself, right? Because you have that to the second power. So you write it out twice and then again go back and use the FOIL method to come up with the answer. So that's kind of how, you know, these examples are working out. So let's, again, just for practice, make sure you guys are able to do this. Let's pick a quick example over here. You know what? Let's do something like, I don't know, 21. And your instructions are, again, just perform the operation and write the result in the standard form. Okay. So as you can see, this is square root of 2 plus 3i, which square root of 2 is a real number. So this is still in your standard form, and square root of 2 minus 3i. So if you again recognize that it's the same two numbers, just with the plus or minus in the middle. So again, remember, these are what we call as complex conjugates. And again, guys, conjugates means, oops, wrong spelling, is when one of them has a plus sign and the other one has a minus sign. They're complex because they both have imaginary parts to it. So in this case, remember, this will come down to where you take the square root, the square of the first number plus the square of the second number. And you literally don't even have to include the I in this case. So in this one, for your complex conjugates, when you are multiplying a plus bi with a minus bi, they turn into a squared plus b squared. So that's the formula we're using. So in this one, what will happen is, because you have the square root on the 2, basically the square and square root will cancel each other out. So this will not turn into a 4. The square and square root cancel out, leaving you behind with the 2. I'm actually going to put that here. And then the 3 squared, of course, is 9, which ends up giving us 11 as the answer. And just to show you, this would work even if you went through the FOIL method, just to make sure, you know, if you don't recognize the numbers or you're not sure, the FOIL method will also work. So for the FOIL method, we'll multiply these guys together. So that's the first, the outer, the inner, and then the last terms. So that will end up giving us square root of 2 multiplied into itself. So that's our first term. Let's see, this is positive multiplied with a negative. So you will end up with a negative square root of 2 times 3i for the middle. Then let's see, these are both positive. So this one will be square root of 2 times 3i. And then for the last one, positive times negative is negative, and we will be doing 3i times 3i, so 3i squared. Now in the middle, if you want, you can go ahead and simplify this. But what do you notice about these two middle terms over here, guys?
They cancel out?
Yeah, very nice. Savannah, yeah, very good. They will cancel out because basically, you know, both of these are, Andrew, very nice. if I clean this up, this would be 3 square root of 2 and I with the negative sign. This guy would be a 3 square root of 2 with an I. Actually, the I should be in the middle. That's another one of those notation things, actually. We put the I in the middle and then the square root of 2. So they're basically the same term. So they will end up, canceling each other out. And as you will see, that leaves us with the square root of 2 squared from the beginning, and then the minus 3i squared from the end. Obviously, same thing happens here. The square root and 2, the second power cancel each other out, leaving us with 2. Minus 3 squared will be 9. Then you again have I squared, which becomes 2 minus 9 times negative 1. Negative and negative makes it positive. 2 plus 9 will give you 11. So even your FOIL method will work. Oh, just remember those 2 middle terms will end up being, those additive inverses we were talking about. So they cancel each other out, leaving you with just the square of the first term and square of the last term. So use whatever method you want to use, obviously whatever you're comfortable with, and it works out just the same. Okay, so that's your multiplication for the complex numbers. Now they actually are talking about the complex conjugates over here. So you can see a plus bi, a minus bi are complex conjugates. When you multiply, they're going through the FOIL method, but basically this is what it comes down to. So if you can remember this formula, you will save your, couple steps of calculation and just go directly to the final answer from there. So that's your complex conjugates. And they're giving you another example here on how you can, multiply the complex conjugates and get your answer. Now we're getting into sort of what we would call as division between complex numbers, but it's a little bit different than, your typical division problem, right? So in this case, we're talking about, okay, so how do we divide a plus bi by c plus di, or, you take the quotient of those two complex numbers. Since c plus di is a number in the denominator, you want to make sure both of them are not 0. C can be 0 or d can be 0, but you don't want both of them to be 0 because it's still the same thing. Division by 0 is undefined. So it doesn't matter what you have on the top, but if the denominator is 0, it is always going to be undefined, and that's going to be true for complex numbers also. So look what happens here, guys, when we're trying to solve this quotient problem over here. You actually take the complex conjugate of the denominator and you multiply both your numerator and denominator by that complex conjugate. So on the top, of course, we end up doing FOIL to multiply a plus bi with c plus di, but then on the bottom, since you're multiplying complex conjugates, we can bring in that formula, c squared plus d squared, and clean that up. And then, whatever you simplify will come out to be your final answer in this case. So they're talking about, when you're multiplying by the complex conjugate with your numerator and denominator, basically the idea is, since it's the same number on the top and bottom, you can cancel that out, and that ends up becoming the number 1. So you're not changing the value of your number or of your fraction because you're technically multiplying by 1, but that's how we end up, simplifying the original expression. And again, you've got examples over here to look at, but let's pick an example here for us to, this is multiply, write the quotient. Yeah, let's take a look here. I don't know, let's look at 36. So you've got 6 minus 7i divided by 1 minus 2i. So obviously, again, we will multiply this by the complex conjugate of the denominator. So since it's 1 minus 2i, its complex conjugate will be 1 plus 2i. So then you end up multiplying these guys together. So we are taking 6 minus 7i and multiplying it with 1 plus 2i. On the bottom, you are taking 1 minus 2i and multiplying it with 1 plus 2i. So we will need to do FOIL on the numerator. And then on the denominator, remember, it will just become a squared plus b squared. So let's see, 6 times 1 will be 6. So, doing the FOIL method, then you are doing 6 times 2i. They're both positive. So 6 times 2 will be 12. So this guy becomes 12i. Then the inner term, so negative 7i with 1 will be negative 7i. And then for the last one, you're taking negative 7i multiplied with positive 2i. So positive times negative will be negative. 7 times 2 is 14. And then, of course, I times I will give you I squared. But then remember, I squared becomes negative 1. On the denominator, since we're multiplying complex conjugates, we'll take 1 squared plus 2 squared. And that will clean up because we won't have any I values left in the denominator. So I don't know if this kicked in any memory or not, but this is kind of similar to what we do with rationalizing the denominator, if you really think about this, because when we are rationalizing the denominator, something like 3 divided by square root of 5, we usually end up multiplying by square root of 5 on both top and bottom. So that would end up giving us 3 times square root of 5. And then on the bottom, the square root disappears and you're just left with 5. And you get rid of any radicals in the denominator. That's kind of the same thing happening here, because you actually don't want to leave any I terms in your denominator. So that's kind of what we are doing here, is because you have that 1 minus 2i in the bottom, we don't want any imaginary number in the denominator of our fraction over here. So that's why you're multiplying by the complex conjugate to get rid of that imaginary number. So it kind of reminds me of, rationalizing the denominator, because again, the idea is we don't want any radicals in the bottom of our fraction. So that's the same thing happening here almost. So now we just have to clean this up. Of course, the denominator will clean up into 1 squared is 1, 2 squared is 4. So that guy will, of course, end up becoming 5. Now on the numerator, we have 6 by itself for now. The 12i minus 7i will combine into each other. So 12 minus 7 will give us 5i. And then your minus 14, I squared will become negative 1. So, obviously that then becomes, keeping everything else, 6 plus 5i. Negative and negative will become positive. So that ends up becoming positive 14. 1 plus 4 on the bottom will become 5. And then combine your like terms, which these guys will go together now. So that's what, 20 plus 5i, and then this is divided by 5. But we actually don't leave complex numbers in this form, because remember, they have to be a plus bi. So they have to be 2 separate terms. So all you have to do now is separate that denominator with the 20 and the 5i. So you will get 20 divided by 5. And then, whatever plus or minus you have in the middle, put that sign. And then 5i divided by 5. So cleaning up your fractions, what will we end up with when you simplify those? Okay, let's see what you have. Very nice, Lucy. Yeah, because Savannah, very good, because 20 divided into 5 will give us 4. 5 goes into itself once, goes into 24 times. And then 5 goes to itself 1 time. So you actually end up with 4 plus I. So nice and clean answer when you look at it. So just remember, do not leave your answer with a single denominator on the bottom. You do need to separate them. And then if your fractions will simplify, go ahead and simplify them. All right, perfection. Any questions on the quotient for complex numbers? Okay. So I'm kind of hoping that as we are going through this review, you are kind of jogging your memory and remembering some of the stuff I'm hoping you've done in your college algebra course. This one here is, again, just kind of getting into simplifying radicals. They're talking about how you can have complex solutions in quadratic equations. And I know when I teach my college algebra course, I definitely include examples where students are able to see that, we're going to get imaginary and real number answers. So again, guys, just remember, whenever you end up in a situation like this where you have a square root of a negative number, just separate that negative sign by using -1, and then the square root of -1 will become I. And I don't really like the way your textbooks writes this. It should be I square root of 3, because otherwise a lot of people have a tendency of putting that I inside the radical. And this is wrong. The I is by itself because we have converted square root of -1 into I. So it doesn't have a radical on it anymore. It's outside the radical. And then whatever was left behind, you put it on the outside. So the notation is, if you had something like, we had 3I without the radical, the 3 goes in the front and then I in the back. If you have a radical, the radical goes after I. So the notation is whole number in the front or integer in the front, I in the middle, and then the square root. So, if you had something like 3I square root of 2, that's how you would write it. So that's kind of the notation you should have, but your textbook kind of does it in its own way. Alrighty, so this one here is just talking about what happens if you are multiplying two numbers that both have a negative sign. Well, of course, each one of those, you can take the negative outside as I. So technically that would be I on the outside, and then square root of 5. When you multiply, I times I will become I squared. Square root of 5, square root of 5 will basically, it's square root of 5 to the second power. So they cancel out, leaving you with 5. I square will change to -1, and you'll end up with -5 as your answer. So they're just kind of showing you this. This over here is a little bit different because you don't technically have two separate radicals. You're combining them into a single radical. So you have a single radical, which means we actually, because remember, this works as a grouping symbol. So you're actually multiplying the numbers on the inside first. So negative times negative will become positive. You end up with positive 25, and then square root of 25 is 5. So just a little bit of a difference in, the notation of the two problems. So they're showing you again, how you would work with examples like this. So this one in part A, again, you will see there are two separate radicals. Of course, each one of them will give you an I, which will come out to be I squared, which will turn into a negative number, a -1. And then once you clean up square root of 3 multiplied by square root of 12, that becomes square root of 36, which simplifies into 6. And you end up getting -6 as your answer. So something similar will happen here. These ones you are subtracting in part B. So for part B, of course, take the I outside. So you've got your I's on the outside. Now you're left behind with square root of 48 and square root of 27. Whatever you can clean up. Now this may be something you may not have done in a while, simplifying your radicals. 48 itself is not a perfect square, right? So it's not like a number like 9 or 4 or 16, which are, 4 times 4 or 3 times 3. You don't have that kind of situation here. So then you have to think about, what can I break down 48 into where it would have, a perfect square as part of it. So you can think about maybe starting out with a 4. So, if you start out with a 4, 4 will break this down into 4 times 12. But 12 can also actually be broken down into 4 times 3. Or if you recognize it straight away, you can break down 48 into 16 times 3. So that tells me, which will be the same result we get from here. 16 is a perfect square. So square root of 16 can be simplified, which of course will give us 4, and then the square root of 3 will stay behind. So that's how they came up with 4 times square root of 3i. And again, if I were writing this out, I would write it as 4i and then the square root of 3. Same thing happens with 27, because 27 will break down into 9 times 3. Square root of 9 is 3, and then you're left with the 3 after it. So that again will become 3i square root of 3. Now here's the interesting part, guys. This may take a little getting used to. The I and the square root of 3 part is the same. So think of that as your x. So technically you have 4x minus 3x, which will of course clean up into 1x or just x. So that's what's happening. You're doing 4 minus 3, which becomes 1. And then you're just left behind with your I square root of 3. Because, that part is not going to change. So they kind of start acting like your, variable x. Because that part stays the same, you're just subtracting the numbers that are in front of it. The last one, as you can see, is basically doing second power. So again, you basically, go ahead and I would just say, clean up that square root of negative 3 into this. Again, they're putting it kind of after. I like to put it in the front. And then go ahead, write it out twice, and then use FOIL to, simplify this. And that's what your answer should come out to be. And again, they're giving you an example to kind of simplify that. But this is what I really wanted to get into, is when you get a complex solution to your quadratic equation. So this one, and again, if you're unsure about what the quadratic formula looks like, that would be x equals negative b plus or minus inside the square root b squared minus 4ac divided by 2a. And your a value is coming from here, so a will be 3. B is coming from here, so b will be negative 2. And you always take the negative sign with the number. And c will be positive 5. So you will see you have negative, which is coming from the formula. So that's this negative here. Negative 2 coming from the b value. So that's the negative times negative, which makes it into a positive 2. Then negative b, sorry, that's b squared. But again, your b is negative. So you're getting the negative 2 minus 4. A is positive 3. C is positive 5 divided by 2a. Again, a is positive 3. So let's go ahead and actually do a very quick example for this quadratic one over here. And let's pick something with the negative number on. Let's do, I guess, 52. Okay, so A would be 9. B would be negative 6. And C would be 37. Our variable is x, so this will be x equals negative b plus or minus square root of b squared minus 4ac divided by 2a. And it's actually that b squared minus 4ac, that little calculation there, which tells you if you're going to get a real number answer, if you're going to get imaginary answers. And it also tells you if you're going to get a single answer or 2 answers. So remember, that's what we call as the discriminant. So now when you plug in your numbers, you've got negative b, so that's a negative sign. B itself also has negative on it, so that's the negative 6. Plus or minus square root of b squared, which will be negative 6 squared, minus 4 times a is 9, times c is 37, divided by 2a, and again, our a value is 9. So cleaning this up, on the negative b part, you have negative times negative c. So the two negatives will become positive, leaving us behind with positive 6. Plus or minus inside our square root, you have negative 6 squared. And guys, look how I put -6 in parentheses and then the square on the outside. Because if you just do -6 square like this, and you plug this into your calculator, you will actually get -36 because the calculator is not recognizing that the negative goes with the 6. So when you put this in parentheses, that means you're doing negative times negative and you end up getting positive 36 as your answer. So be careful when the b itself is a negative number. So negative times negative will give us a positive 36 here, minus, then we're doing 4 times 9 times 37. So that'll come out to be a fairly large number, 1332. Divided by 2 times 9, of course, will give us 18. Now you will see when we do 36 minus the 1332, we will end up getting a negative answer in there. And that's how you know you are actually going to end up with an imaginary solution, because anytime you end up with a negative for that b square minus 4ac, that's when you end up with an imaginary solution to these quadratic equations. So this will come out to be -1296. Is 1296 a perfect square? Yes, it is. Awesome. So 6 plus or minus, you do have to clean that up. So remember that negative, you can imagine that as being a -1. So that negative sign will actually come outside as square root of -1 as I, leaving us behind with a positive, square root of 1296. What is square root of 1296?
$36.
Yeah, it is a perfect square. So when you take square root of 1296, you will actually get 36. So this will become 36i over 18. And then remember, as I was telling you before, we do need to simplify this. So you will separate that as 6 divided by 18 plus or minus 36 divided by 18, and then the I. And then, of course, we'll just need to clean up our fractions. What will 6 over 18 become? Very nice, Andrew. Yeah, because 6 goes into itself once. 6 goes 18 into 6 3 times. So that will be 1/3 plus or minus. And then what about 36 divided by 18? Yeah, very nice. 18 goes into itself once, goes into 36 twice. So that will become 2i. So, in algebra, we normally write it as 1/3 minus 2i and 1/3 plus 2i. So you will have two answers for your x variable here. Wow. 4. So you can write it as with the plus or minus sign, which I don't know if WebAssign takes the plus or minus sign. If they don't, then you may have to write it out separately, once with the plus sign and once with the minus sign. Question on this, guys? Okay. So again, remember, this section here, 4.1 is review, but you do have homework assignments on this. For some reason, it's not showing me the list. There we go. So you will see that you do have a homework and a quiz on 4.1, because again, like I said, because it's been a little while since you guys have probably done complex numbers, I did want to give you a chance to, refresh it, go over it again. So that way, when we start using complex numbers in 4.3 and 4.4, you're not feeling lost, like, oh my God, what am I supposed to do with these numbers kind of thing. So we have two sections, from chapter 4 left behind. And even though they are not very big sections, I honestly don't know if we can finish both of them in one day or if it'll take a little bit longer than one day. So I'm again going to play it by ear because like I said, I'm not sure. So we're definitely not taking the exam on the 18th. for now, I will transfer it to the 20th, which will be a Wednesday. And for any reason we feel like on Monday we need just maybe a little bit more time, I will move that. But if we can finish both 4-3 and 4-4 on Monday, do you guys need more time than just 2 days to finish the homework? Should we move the exam to the 25th, or would you be okay with the 20th if we finish chapter 4 on Monday? Because, you know, I don't want you to feel like you're rushing through homework to make that deadline. So how do you feel about it? So, you know, I can kind of base it on that. Should we move the exam to the 20th or to the 25th? Because, you know, we can start the next chapter. Okay, Andrew, you're feeling like you would have to rush. So it's better to do the 25th. So that way you get the rest of the week to finish the homework and be ready for the exam. I can do that, not a problem. So let's do that. Let's keep the 25th as our exam. And Alicia, that's what you also said. So we'll keep the 25th. So whenever we finish chapter 4, you should still have enough time to get the homework done. And then, you know, if we finish chapter 4 on Monday, let's say, then we'll at least start chapter 6 on Wednesday. Okay, so just kind of keep that in mind. All right, guys, if you have any questions, I'll be happy to answer them. And if not, I will see you guys on Monday. So have a wonderful weekend, everyone. Be safe and see you on Monday.
You too.
Take
Thank
care,
you so
guys.
much.
Thank you. Be careful. Bye, everyone. Hey, Melanie.